Hello, welcome back to the milestone session, our last talk of REAC. Y'all have stuck it out through all of the exciting talks, all of the learnings, and been resilient through Zoom crashes. So thank you for that. Our final talk will be from speakers from Saber Interactive. Max Bukhalov is a graphics programmer at Saber Interactive, working on in the game industry for over 5 years. He helped to ship such games as World War Z, Halo: The Master Chief Collection, and Warhammer 40K Space Marine. At the moment, Max is working on Roadcraft and the upcoming Toxic Commando and Jurassic Park Survival. He is joined by Yegor Orochev, who is a graphics programmer at Saber Interactive, working on rendering technology for the in-house Swarm engine for 4 years now. Yegor has been involved in development of such games as Warhammer 40K, Space Marine 2, Roadcraft, as well as the upcoming Toxic Commando and Jurassic Park Survival. Yegor's main areas of interest include topics such as GPU-driven rendering, programmable materials and shaders, data-driven game simulations, rendering tech tooling, development workflows improvements, modular and reliable game engine architecture. You can see that both of them are tailor-made for speaking at REAC. Let's welcome them.
Hello everyone and welcome to the talk Geometry Rendering and Shaders Infrastructure in Warhammer 40K Space Marine 2. My name is Igor and today alongside with Max we are going to give you an insight into our rendering engine development used to ship Space Marine title. Just a quick disclaimer about this talk. This talk aims to give the context of the engine development and project's features. We want to focus here on rendering engine architecture and systems design, and there will be no hard science nor state-of-art rendering techniques, so it's more about not how to do it right, but how we did it and what lessons we learned from it. We at Saber use our proprietary in-house engine called in recent years Swarm engine. This engine features a full development toolchain. It counts over 2 million lines of code. The engine itself is supported by the core team, which counts over 130 engineers, and the actual projects which are developed, project games which are developed in parallel, are developed by game development teams, which count over 450 persons, excluding, of course, outsourced teams and satellite studios. We, at the studio, have a primary focus on game development, so the engine as a technology not released to public as is. Saber has developed a lot of projects using own technology in past 2 decades, but we want to focus our attention only on recent one. The World War Z game was released in 2019. It used the first version of the Swarm engine, and the recently released Space Marine title used the next version of the engine called Swarm Engine 2.0. In order to do such a transition, we have to rework and a lot of engine features and aspects, and some improvements are game specific, but some of them are relevant for almost all modern games. And in this presentation, we want to focus our attention on 2 topics: geometry rendering pipeline and shaders infrastructure. So let's get started from geometry rendering pipeline. Historically, the previous generation of the engine targeted PlayStation 4, Xbox One, and PC platforms. The frame rate was locked to 30 FPS. Engine used a forward plus rendering pipeline with 2 frames of latency, and visibility test was done in computer shader, and multi-threaded common buffer generation was used. A very good overview of the rendering pipeline and Horde technology was given in the talk at GDC conference by Anton and Denis, so check it out if you want. This version of the engine has the following frame structure. On the main thread we fetch user input, then in fast batch. We update transforms and prepare cameras. Then, as soon as cameras list ready, we from render thread submit it to GPU for visibility culling. And then, while game logic updated, what is a costly process, we read back results and then use these results to collect render requests and prepare them to be submitted on the render thread for actual shading passes on the GPU. In terms of code organization, we have heavily object-oriented rendering code. The core primitive for this code is anim instance class. It is a based object used almost in all rendering code. By its purpose, it acts like a bit mesh filter and mesh renderer in Unity and a primitive scene proxy in Unreal Engine. And we use this object to render almost all types of geometry, animated geometry, vertex instance vegetation, static scene, merge vertex soup. And for next generation of projects, we have new requirements which must be addressed. First of all, for geometry and environment, we still want to have indoors and outdoors locations. We want to have details in meshes where we can have more than 60 million triangles before any culling. We want to support hydro distances, and we will support dense vegetation, where in some cases we will have more than 10 instances per meter squared. In terms of simulation and shading, we want to support a large amounts of animated instances because it's the key feature of the game, the swarm technology. We want to support all shading features from World War Z game as well as new ones. In terms of hardware, we want to target actual consoles, and we want to support both frame rate modes, 30 FPS quality mode and 60 FPS performance mode. And so the main dilemma is our anim instance class. It's a God class anti-pattern example. This class has a lot of architectural flaws because a lot of systems use it and a lot of systems depend on it, and not all of these systems are related to rendering engine. Moreover, this is quite a heavy class. It makes a lot of heap allocations. That's why it has a lot of scattered in-memory data access, what hurts performance in the end. And we need to somehow evolve the system, and rewriting everything is not an option for us. Well, what options do we have? Not many, really. We can leave everything as is with minimal changes. However, this path scales very poorly, and early performance tests with preliminary art setup show that we had a really poor performance both in time and memory. The second option is bold move forward GPU-driven path. This removes almost all CPU overhead. However, this path requires a very large refactoring of almost all code related to drawing geometry, and we cannot afford such option for us. And the path in the middle is a hybrid rendering pipeline. It unlocks both GPU performance, benefits from CPU flexibility, but it has its own drawbacks, but we can handle it. That's why we chosen a hybrid renderer approach. It conforms our conservative render evolution philosophy, so we can focus on game features first. This path reduces the amount of refactoring we have to perform, so we can keep intact our legacy structures and somehow adopt it for new needs. And with this path, we will be able to support CPU features as well as get GPU performance. The first main step that was taken is anim instance decoupling. We removed instance-related data for rendering from an instance and moved it into specialized instance data manager. This way, anim instance API remained unchanged, so we avoided client code rework, as well as we get some benefits So now we can create instances without creation of heavy anim instance, and now we can use this anim instance as proxy for draw calls generation. Although anim instance is still complex class, but its refactoring is out of our scope. By making this small change, we unlocked the implementation of hybrid renderer. As you can see, a fairly small number of elements were changed. So the key ones are highlighted. And now, after camera release preparation, we submit not only visibility culling, but we submit our GPU instancing solution, and then we read back those results on CPU and use them to prepare draw calls. In terms of code organization, we have the following stack of systems that participate in hybrid renderer pipeline. Logically, the stack is divided into backend and frontend part. Backend is more related to geometry rendering itself, and frontend is intended for clients usage. So let's have a look at the backend. The core of the backend is instance data manager. Conceptually, instance data is a large structured buffer of float4 values, which is available on GPU. Logically, this buffer is divided into two parts: static data for GPU instancing and dynamic data for CPU instancing. This system performs the whole cycle of data management. It allows to allocate, delete data, update, and provides allocation for instancing payloads. The static data itself divided into two parts. The first part stores data from static geometry placed in the editor. This part consumes 5 megabytes of memory and can fit up to 300,000 instances. All of this data is packed on scene cooking and loaded in runtime at scene loading, so there's no streaming in runtime. The second part is procedural placement pool. This pool has size of 6 megabytes and it can fit up to 400,000 instances. So this memory used at runtime to allocate the cache instances generated in our custom compute shader for placement. The instance data itself fits into float4 value, and we use here aggressive packaging. Dynamic data management is a bit more complicated. The actual data source is managed by a front-end system, so the source of data is allocated and stored in the format that front-end operates it. And upon creation of instance, we assign an archetype to the instance based on the rendering features it uses, and we allocate a unique instance ID for this instance to later fill the rendering side instance data. The actual data stored on the rendering side in special format prepared for geometry rendering, and all instances are stored on archetype basis, and we manage additional layout offset tables for this data packing or in shader because there is no gaps in these data features. For instances that will be rendered on this frame, we copy their data from CPU to GPU using Scratch buffer. This buffer has a size of 10 megabytes on average. On consoles, this copy operation is cheap due to a uniform memory architecture. On PC, via PCI Express, the copy takes up to 1 millisecond, but we hide this latency using async compute transfer. This way, we simplify data management, allocation, fragmentation, and so on. And since game code updates dynamic data really frequently, we do not experience a strong loss of performance here. The final part of instance data management is the allocation of payload data needed for rendering. The payloads for GPU instancing are allocated using compute shader. Here we store payloads for all cameras. And then on CPU, in our draw calls batching system, we allocate payloads for dynamic instancing of CPU instances. Single payload data fits float4. It captures information required to render a single instance into a single camera. And here we have slightly different layout for static and dynamic instances because these instances support a bit different set of shading features. And now we have covered our instance data management, and now we can move towards actual draw calls building. We use GPU powered culling in Compute Shader. It is almost the same as was in World War Z title. The whole processing it takes works under 0.5 milliseconds. Here we support culling of up to 100,000 boxes. We have on average 1,000 manual low poly occluders for occlusion culling, and the actual culling process outputs the result data either in two ways. One part goes to readback for CPU instancing, and other part is propagated further for GPU instancing. On the CPU, for draw calls creation, we have made a new system for draw calls batching from scratch. The purpose of this system is to collect draw requests from client systems, store them, filter, sort, and group, and finally prepare parameters for draw calls. In a sense, it's similar to Unity SRP batcher and Unreal Mesh draw common batching. The key concept of this system is a single draw request. This structure captures need to draw a single split of an instance into a given number of cameras. This structure holds all information required to identify it instancing bucket, and we can have up to 10,000 draw requests in a frame without any performance losses. On average, on scenes, we have 4,000 unique buckets for instancing in total. For draw request collection, we have written a custom queue using thread local storage optimization. All requests are collected inside chunks allocated from pool. Each chunk can store up to 64 requests, and whole pool consumes under 1 megabyte of memory, what's quite cheap. Then all requests are from chunks are unfolded into a single special buffer, where these requests end up grouped together by bucket type. This buffer is quite small, and it uses under 1 megabyte on average. Then the final step is to sort and aggregate all draw requests for buckets into some parameters, which then will be used to generate actual draw calls. We use on average 100 buckets on scenes, and allocate on average 1 megabyte of payload data for all of these buckets for instancing. And this payloads data is allocated directly in Scratch buffer, which will be later copied to the GPU. On the GPU, instancing is done in our special compute shader. For this shader, we have written special culling structure. In this structure, we store visibility blocks. Each visibility block stores a number of instance blocks. A single instance block groups together instances of the same type. We use this structure to determine visibility of individual instances, and then process each instance, evaluate LOD, opacity, density reduction, and so on. And then this shader outputs a table of draw calls for draw calls generation on CPU. This shader is executed after visibility culling. The whole shader works under 0.4 milliseconds. We support here FRASTM and HZB culling for individual instances. We support up to 16 cameras, up to 8 LOD levels, plus additional billboard index per mesh, and we can have here up to 2,000 unique mesh types. The readback data for single camera is under 1 megabyte on average. And the final step is draw calls assembly. This system is just a thin layer just above hardware abstraction layer. A single draw call or deep um, stores minimum required information to perform a single instanced split rendering with given material into given camera view into a single shading pass. All these draw primitives are captured, collected, and then sorted and recorded into command buffers. The assembly of draw calls is performed according to the following scheme. The vertex format and vertex buffers come from split. Shaders list comes from material. Each shader can render it into a number of predefined engine shading passes. An example of such passes is Z-pass, G-buffer distortion, transparency, shadow map, and so on. Then this information is used to get pipeline state objects. Then we use this information to fill material cons buffers with shading constants and texture indices, and then we finally create our draw calls. Instancing payloads come from our CPU and GPU instancing systems. So that's it for the backend part, and now let's take a look at the frontend part. The frontend for drawing actors has not changed. It uses anim instance under the hood, and it conforms existing client code. We have custom script bindings in form of a scene actor prop. This prop can be used in our scripting solution. This prop allows to modify materials on individual splits, show height individual parts of geometry, tweak some parameters, tweak transforms, and so on. It's very flexible, but of course such solution suffers from memory and overhead and CPU performance if you have too much actors on the scene. To draw ECS entities, we have written from scratch entire ECS frontend for our system. This frontend can handle up to 10,000 entities for drawing. It uses more than 20 custom components for rendering and requires more than 40 systems to process these entities. We use our proprietary in-house ECS framework for this ECS rendering. Components are declared in special ECS files in data definition language, and then we use a generator tool to auto-generate C++ with all required boilerplate and beta information for runtime and editor. ECS systems are declared in the same ECS file using the same language, and the same generator is used to generate systems declarations in C++ with required meta information for the system's scheduling, and also it generates additional stub method which can be filled with actual C++ implementation code on engine side. We have very positive experience working on ECS render. Basically here we re-implemented a lot of logic from anim instance, and it worked extremely well for us. Yes, we had to add some features from anim instance to ECS render, but it has been done on demand. Also, we were able to split our work among rendering and engine team here. We get multi-threading out of the box due to our ECS framework. Of course, we experienced some minor problems. We had divergence of logic in ECS and anim instance. We have some thread safety problems. In some cases, we had poor performance on heavy entities, but it was fixed during the polishing phase of the project. And if you want to learn more details about our ECS framework in general, check out Sergey's recent talk at the GC conference. An important part of pipeline is static meshes rendering on GPU. In order to achieve this, we implemented custom pipeline for that. In this pipeline, actual assets are modeled in DCC tool. These assets are modeled from individual small, often duplicated elements, and then with special markup, we export these assets into prefabs, and all individual elements are deduplicated and exported as individual meshes with individual LUD and rendering settings. And then these prefabs are placed on scene in our level editor, and all of these individual pieces become individual GPU instances. And for each individual instance, we apply individual LED logic in shader, and here we can handle up to 250,000 instances. And all of this data is automatically packed on sync cooking and then loaded in game runtime. Our placement system allows to generate on-demand instances in Compute Shader. For this generation, we use special generation masks, which are painted using custom brush tool in the editor. And with additional distribution settings, at runtime, we generate these instances on demand. The generation process is quite costly, but we amortize it using cache. And on Space Marine 2 title, we had roughly 200,000 instances in our cache. Scattering tool allows to scatter some small meshes and debris in level on geometry. For this, we use a special scattering brush in the editor and some distribution settings which allows to generate these instances, and all of these instances are generated in the editor and then saved on disk and loaded on scene loading. For these scattered instances, we have additional logic for density reduction, and of course all of these instances go through our standard GPU instancing pipeline. So now we have looked at the geometry rendering front end. Now we need to understand which rendering path to choose. Because rendering path now is defined by the client code, by front end of the system. Our rendering engine does no automatic switching between CPU and GPU rendering paths. For this, we have defined the following set of simple rules for ourselves. In most cases, static geometry is sufficient because it covers most basic use cases. If you need to simulate or control a large amount of entities, you should use ECS path. If you need full scripting support and rich features, and you know that you won't have a lot of instances, the actor pipeline is your choice. Other cases are too specific and handle it on individual basis. Of course, such solution has its own drawbacks. In worst case scenario, all scene ends up in all actors, so it requires careful performance profiling. In the conclusion on geometry section, we evolved system to suit title requirements. Instancing everything rule worked for us, and hybrid render pipeline worked well. We avoided large refactoring, and we didn't break any existing code. And with this pipeline, we were able to perform incremental implementation with individual steps evaluation. System front-end also worked well for us. We supported ECS rendering pipeline, and also we came up with a convenient editor workflow, which is more artistic driven for our static geometry. Of course, there is a number of things to consider. CPU bottlenecks draw cost generation in some cases, what requires manual art setup tuning on project side. Also, we now have to maintain both systems, which will diverge at some point, what isn't good. Performance of our culling solution is still debatable because manual occluders are not always applicable, and in some cases, some instances are too large to perform precise occlusion culling. But now it's reasonable to move towards fully GPU-driven rendering pipeline. Half of the work is done, but there's still much to be done. So that's it for the geometry section, and now I give a word for Max.
Hi everyone, my name is Max. I will give you a talk about our shader infrastructure in Space Marine. Shader system is still pretty much the same compared to the system we visit with. Going into the development of Space Marine 2, we knew that the game required complex materials and quite large scenes. It was important to us not to get in the way of artists and developers and at the same time hold on to the performance. We wanted to keep the principles of the system we already had, like simple shader authoring, simple maintenance, that means easy to inspect, profile, debug, or tweak and tune shader code, keep logic in one place when possible, easy shader interaction from C++ code, as well as simple material parameter setup for artists, fully automated build process to minimize latency between committing changes and getting them, and also getting testable builds as quickly as possible was really important to us. We also didn't want to rewrite the design of shader system, and we wanted to work with what we got, since we didn't really have resources to spend for redesigning the whole system. My part is divided into 3 chapters. First, I will introduce you to the architecture of our system, then I will briefly describe how our build process works, and then I will tell you about pipeline precaching and how we get around this problem. We write our shaders in HLSL with macros to be able to support all 3 platforms, PC, Xbox, and PS5. Writing in basically state HLSL allows us to write code that will go straight to the compiler, which allows easier shader debugging on all platforms. We write our shaders in Uber approach. Most of the feature branching happens using preprocessor and defines, which allows us to save on shader binary size and avoid unnecessary branching in code. We have fixed file extensions for our shader files to make it easier to navigate through the code base, which is around 100,000 lines of code. A path in our terminology is a logical unit of shaders, sort of like a pipeline. It's quite easy to confuse it with frame stages like depth pass, debuffer pass. That is not really what it is. It's not where in the frame you enter, but rather what. Example of passes of our region is like SSL, particles, water, or lead skin material pass. Pass consists of 3 different parts: shaders, of course, pass setup, and pass desk. Pass desk is a set of variables that influence how pass is set up. Desk, as well as setup, is written in text format or own format, like JSON or YAML with syntactic difference. There are quite small set of types the variable can be declared: bool, float, int, num, color. These parameters are exposed through our tool to artists for materials, as well as exposed for programmers through auto-generated structs. A pass setup is a description of a pipeline that will be used for draw or dispatch. It consists of several sections, and for every parameter there is a condition that depends on the parameter described in the pass desk, or depends on common parameters like shader option, platform options, material with layer information, UV sets, etc., or split information like geometry information, vertex layout. So first section, real order doesn't matter. It's done for presentation purposes. Defines, we can maximum declare 256 defines per pass. And there's a declaration and the condition, and the define is set when condition evaluates to true. The same logic applies to pretty much all the sections. So there is how we define vertex format. There is our render state, render target formats. We also have a render flags, which is not directly corresponds to pipeline state, but it's rather a flag that we can put some logic into the engine, and we can depend on that parameters. For example, in what queue draw call will go, in depth queue or debuffer queue or transparent queue. We can affect sorting order, or we can basically write pretty much every type of logic we can. So it's very agile feature that allows us to be very agile with our draw call queue formation. We also have state flags and usage, the small sections that describe what shaders are needed and how pass is pass material or not, should be pre-cached, how it is processed during C++ code generation or build process. So passes can be material or engine. Material passes is a very small subset of passes that can be put into materials. 90% of materials are using only one, which is quite heavy, very uniform. And during pre-process, we can actually use all the permutation we need. Since we depend on materials, we can walk through the scene and derive all the information from there. Examples of such passes like vfix pass or lead skin pass. We also have engine passes. The parameters are set up from C++ code space directly. Not always computes, but can be computes, of course. All the computes are actually engine passes. And since all the parameters are set from the code, we cannot deduce permutations. We ought to enumerate all the possible defined sets to store it in cache. Example of that is fill. Fill is simple shader that fills both a texture or copies one texture from another. And there are quite heavy passes that are engine passes in our system, like terrain, water, particles, trail. All of them are engine passes. As I mentioned before, there is a code generation in our system. We generate code for every pass. We generate structures like shader desk, which corresponds to pass desk, as I showed you before. We also generate some other structures for common parameters. We also generate functions to avoid boilerplate, which help us to use define sets, render state, render flags, or even retrieve a good signature, which we also auto-generate and put into auto-generated code using our shader reflection system. So retrieving a pipeline state is relatively easy. It's just filling a structure with parameters and a few function calls. In terms of caching and storing shaders, we have a local cache for dev purposes only. It's for a runtime compilation. It is not shipped, and pre-built cache, which is shippable, contains all the necessary data to the retail version of the game. For every pass, we generate a SDC file, which is compressed blob collection, which contains shader binaries, pipeline state collection for material passes. It's like structure of 200 bytes, which is, has all the information that we can deduce pipeline state desk from. And we also store some meta information for validation purposes. Some statistics for shader cache, PC, DirectX 12. For material passes, total we have 314 megabytes of compressed data, total of 11,000 unique binaries. Every binary size uncompressed is 42 kilobytes and 27,000 pipelines roughly. For engine, we have 406 megabytes around that, which is a lot more than material passes. We have 38,000 unique binaries, which is more than 3 times more shaders than material ones, and average binary size is around 17 kilobytes. We also have our own authoring and editing tooling. We have Shader Studio, which is our own shader editing and authoring tool. It used to be a desktop standalone application. Now it's Visual Studio extension, and some of the features that Shader Studio had moved into CLI tools that Shader Studio, the extension, calls. So we author, we edit shaders in Shader Studio. Then there's some commands we can execute. For example, we can copy files, we can tell engine to hot reload, we can send signal to engine so shaders are changed, or we can execute through shader generator a more complex tools like code generation for C++ or shader reflection generator. This is all done through CLI tool, and this can all be communicate to the engine. For example, shaders are changed, reload them, and recompile them. An engine, in the other hand, can communicate back and say what the errors were. So all the errors, all the code in Shader Studio, while like heavy lifting stuff is moved away into CLI tools. So regarding our build process, how does it work? We have quite different paths for engine passes, material passes, since material passes depend on scene processing, engine passes are not. We just enumerate all the possible permutations of shaders and compile and store them. We don't generate pipelines for engine passes. It is too much of computation. We just cannot afford too many memory and build process overhead. So it is important for us to have a relatively quick build process. So all the processing that can be done at the same time is parallelized. For example, scene processing is done at the same time. Every scene calculates at the same time. So since scenes don't depend on each other, we can greatly improve our computation speed. So combination generation is also doesn't depend on the scenes, so we can parallelize those. And then we go into Shader Cache Console stage. Shader Cache Console is one tool that does quite a lot of things. I will describe what it does in stages. First of all, it gets all the combinations. It checks previous shader cache and checks shader sources and determines what passes need to be rebuilt. We have sort of like incremental compilation approach. We recompile just what we need. Then we format batches of shaders and distribute them along our workers to compile. Then we get all the information back and we export it on per pass basis. Regarding timings, generating combinations for engine passes takes around an hour and a half. Scene processing takes around 25 minutes for every scene, and generating combinations for the scene takes around the same time. A shader compilation, that is everything from shader cache and below, takes around 2 hours. Compiling for one platform takes around 10 minutes. Importing and processing for incremental compilation takes around 20 minutes. Rest is exporting, which is really heavy and slow due to PIT-Bs handling. It is a very weak point in the system right now, and we didn't solve it at Space Marine. We solved it in Roadcraft, which is our IM release like just in May, and the whole thing optimized from 2 hours to like 5 to 10 minutes. The total time from start to finish is 5 hours, which is quite a lot, but is relatively manageable for us. We were able to ship with this quite easily. So what's the problem with this approach? First of all, we have 31 scene, not including tests and dev only scenes. Each scene has around 3 to 4K unique materials. Each total condition from past setups is around 2,000. So generating all permutation for engine passes is a very demanding tool. So all of this can easily get out of hand if you miss one thing or another. For example, you add some defines here and there. It can quadruple or at least double your build time. You add a lot of new scenes, dev scenes, and can also increase your build time, even before compiling stage is begin. Byte separation to include files, so shader authoring is also can lead to slowing down build process. So by the utilization of incremental build approach. So you have to be very mindful of everything that is going on here to be able to ship within a certain ship the game and have a build process that is quite manageable and you can live with. In terms of build time, there's some things to consider for every stage. Collect scene info stage. You need to keep number of scenes reasonable, as low as possible. You need to process data at the same time if you can. Also, if you can remove duplication from scenes, you should do that. We have a fake scene for that, for generating defined sets and pipeline sets. Keep test parameters and conditional setups quite low. Lower the conditions, lower the computations. It is best to split a pass into two or more sometimes if it logically makes sense. It's reduce computations and permutations, especially it's true for engine passes. So for compiling stage, there is no much to add besides use parallel compilation and keep incremental compilation in mind when you separate your code into includes. So considering memory, there's pretty much the same points because build time and memory goes almost always hand to hand. So in terms of collect scene information, you need to collect only what you need, not to duplicate any parameters or templates. Use something like common scene, fake scene, or something in this area. In terms of generally defined sets and pipeline sets, keep shader binaries permutation reasonable, lower the shader binary counts, lower the total memory size. In terms of compiling, just don't forget to compress. There is no reason not to do it. Just use any types of compression. It will make a little bit, but still a difference. So now onto the topic we start with the modules, pipeline precache. First, what it is, why need to precache, what we can achieve with precaching. Precache pipeline creation on PC can cause a lot of CPU spikes because CPU heavy operation. It can easily take 50 to 100 milliseconds if you have really heavy shaders. So it can cause a lot of spike if you create during your CPU render thread. It can create a lot of stuttering. So the solution for this is quite easy on a high level. You just don't want to create pipelines during runtime, during gameplay runtime rather. You just create it during loading. So no pipeline creating during gameplay, no spikes, everything happy. Driver will cache it for you, so next launch even loading will be faster. And sometimes you can even unload shader binaries after loading, so you save up memory during runtime. So what we have before Space Marine? We have precache for material passes already, so build process was computing our pipeline sets, and we could during loading precache all the material passes. We had 4+, so shader binaries for materials were very large. We moved in Space Marine to deferred, so shader binaries for materials decreased in size, and so precache for materials didn't really affect us. It was already there. It took around 2 to 3 minutes to precache it all, which was quite satisfactory for us. For engine passes in VVZ was implemented a manual cache. It is a system where QA collect during playthrough all the information of used engine passes, dump it all in some file, and then this information is used later on during build process or even during launch when you precache all the engine passes you need as well. It complicated our build process a bit because it was used in our build process. It was quite unstable. Serialization was binary. It was really shaky. One small change renders all the cache invalid, and you need to ask QA to run through again. So we quickly realized after VVZ even that this is not the way we want to live with this system, with this approach. Code was stripped, but after launch of WarVZ, we didn't really monitor this issue. We didn't profile it, and we only realized that we have a problem a few months before the release. And it was quite a lot of stutter from engine passes. So if you look at the graph, it is some profiling session from one of the scenes from Space Marine, and it is shows how many milliseconds we spent on creating pipelines during each frame. As you can see, sometimes it spikes to like 300 or 250 milliseconds, which is really large spikes. Very noticeable, very annoying. So there was really two ways we can deal with it. Each has pros and cons. So the one way is to enumerate all the possible combinations for pipelines, as we do with materials. It just works out of the box, but it was hard to implement to be able to allow us to compute it in a certain period of time. It was a lot of permutations of pipelines. Also, there was a lot of memory overhead, and it could easily get out of hand if you add some more parameters for desk or move some code around related to shaders. So it was a really unstable system. And we have manual cache approach, which is quite easily to implement, but it slows down the iterations. It's tricky to design right to avoid all the pain you get from this. It's not guaranteed to collect all the pipeline states, so this is quite a huge problem. And changing the art or shaders can easily render cache obsolete. So what we chose? We chose manual cache mainly because we didn't have a lot of time, and the issue really got out of hand. But we did some things differently. We profiled and narrowed down pass lists that we wanted to cache engine passes. So we focused on like 5 of the passes that really cause huge spikes during playthrough. We store pipeline in text format. It's easy to invalidate on a pair pipelines basis, so there is no like binary serialization problems that offsets are moving around and the whole binary is useless. Now you can invalidate on per pass or per in pipeline basis. It's easy to hand fix if needed, if there's some mistakes. You don't need to ask QA to run through the game again, which sometimes can take even days. And at the time we encountered this issue, art was pretty much ready at that time. Cache wasn't outdated for a long time. So that was a plus, and cache was collected only for shipping builds to avoid delays for QA to run through the game. But the cache collected still could be used and was used in dev builds, and it helped with the spikes. It didn't heal all the wounds, but it was helpful for sure. Overall, not the prettiest solution ever, but it got the job done, and we managed to ship the game with this. Overall conclusion, considering precaching. Don't forget about this issue. Try to keep it in mind. It can you can really struggle if you find out quite late during the development process. Try to regularly profile the issue and keep stats even if you can, like every other week or every other day. That way you can find what and why went wrong really easy and really early on. And sometimes ugly solution is the way to go. Sometimes you just need to get things done, I guess. So conclusion to shader infrastructure. We managed to ship more demanding game with little changes to the system. We enabled artists and developers to create with little limitations, managed to save within a certain performance limits, and learned a few lessons about managing precaching performance. Thanks. I wanted to thank everyone who participated in rendering engine development. It is a rendering team, of course, but all the work was mentioned here wouldn't be possible without engine programming team, tools team, infrastructure team, technical art department. Huge thanks for them. A huge thanks to them. And special thanks to conference organizers and to our graphics and technical director, Denis Latkov, for the presentation supervision. I guess it's time for a Q&A.
Thank you, guys. I want to thank you for your awesome talk, and especially for the real stories behind the many decisions that you've done in your architecture. It was very clear that sometimes you clearly see the perfect solution, but it's not the perfect choice for shipping. And that really came through here along with your design choices. I personally found the mixture of pragmatism and ambition super inspiring and interesting. So we have a ton of questions. Let's dive into the questions folks submitted. And I also have to say thanks to everyone who fought valiantly for the Quatluz Prize glory. Well done. Michael, of course, will be the arbiter for that. So we have questions that are per section, and I'm going to kind of ping pong between the geometry and the shaders. So for geometry, Yegor, question to you and I apologize if I mispronounce the name, I'll do my best. Zinedine Amazuz, when is the static instance grid computed?
We use regular grid for instances placing, and basically we pack all instances on sync cooking before the game shipped. So it's the time when we build our spatial structure and group it. So in runtime, we just load it directly into memory and do no spatial structure build at runtime.
Thank you. Now to you, Max. This is a question from Tian Ning. You mentioned material passes are added to queues. What are these queues? Are the queues selected by the artist or deduced by the code?
These are queues that draw call queues that are separated, like where how do I say it correctly? Basically, in terms of example, I hope I understand it, but explain it better. So we have like depth pass, the depths, all depths draw call go in that specific queue and are executed at the same point in the frame. So this type of queues we have fixed. I think in Igor part of talk he mentioned all the queues we have on the slide. So let's sort of like depths, G buffer queues, or like transparent draw calls. So this is our draw call queues that I was referring to.
That's awesome.
Hope I answered the question.
And if not, there's always Discord, because questions can be asked upon your answer. Okay, back to you, Igor. Tom Everard is asking, HDB is using reprojected depth. Does the entire F+ pipeline skip writing out depth instead of opting to reproject when needed?
Yeah, just a remark, we now currently use deferred plus pipeline. Forward plus was used in World War Z title, now we are shifted to deferred one. And now we have in our engine depth prepass for optimization, and for occlusion culling of for next frame geometry drawing, we use a previous frame Z buffer and reproject it and build our HZB with occluders rendered into it. So I hope that's answers the question.
Thank you. Max, Michael Tsukanov is asking, was shader compilation time in consideration when architecting shader infrastructure? Were there any optimizations in that domain?
Shader compilation was quite already optimized at that point. We have quite a optimized distributed setup for compiling. We use a fast build, so we compile shaders through batches, like 15 shaders at a time. We found that optimal count through a lot of worker machines. So as I mentioned in my slide, compiling all the shaders, both engine and material for DirectX 12 or for on PC takes around 10 minutes. It's not really the problem compared to the other stage like exporting, which I mentioned takes around hour or two even.
Thank you. Igor, back to you. From Adam Sawitsky. You mentioned reading back shader results on the CPU. I guess you don't wait for them, so these have 1 frame of latency?
Yes, we're waiting for results basically just around 1 frame. And because we have overall 2 frames of latency, for us it's okay. Yeah. Of course, we hide this latency because while we are waiting for the result, we basically render the previous frame currently on CPU, submitting draw calls to the GPU.
Thank you. Max, back to you. Another question from Tian Ning. It looks like the setup stuff is specified in JSON. What kind of validation is done for the setup to prevent crashes and when?
It's not actually in JSON. It's our own format. It's like PS section. It's called internally, but it was created long before JSON or YAML was really a thing. It carried on throughout our like lifespan of the engine. But the validation of the format is done when the actual tool parses it. So parsing happens when the C++ code is generated. So there is a tool that looks at that file and then executes it. So that tool is executed through shader generator tool. If you remember that scheme with our toolchain. So if something is wrong, it will like tell you in the shader studio or authoring tool. It will write that there's parsing error here, like at the specific point. So there's also one in shader building stage. So when we generating combinations, we also parse setup files and desk files. So there's also error could be made there, and this this handling also happens in that tools, in that set of tools, but errors will appear on the build process like logging stage. So if your build process fails, you open the log and see, oh, that I made a mistake in the certain set of file in the certain space.
Thank you. Igor, we have a couple of questions on the ECS. That, of course, was one of the therapy panels. Questions are pouring in on that. And so I'm going to start with Zinedine Amazou, and we only have a few minutes. So if I understand correctly, your ECS lives alongside the scene actor system. Do you have a long-term plan to migrate fully to ECS for the game logic and or rendering?
Unfortunately, currently, yes, we have our actors pipeline living alongside ECS. Basically, ECS lives in a separate ECS world. And I think it's better to address this question to Sergey, but we have recently talked about that. And unfortunately, back in time when we had this talk, there were no plans to remove entirely actors framework because of basically legacy issues and because of its a lot of code, a lot of scripting related code, a lot of tools depend on this part which interacts with actors and so on. So at this point, it seems like it's some kind of pointless refactoring just in order to remove actors. In fact, on Space Marine 2 title, all critical and performance-heavy work was shifted to ECS framework, so we basically had no issues with actors pipeline. In terms of rendering, of course, it's always better to have one place when one system which renders your objects, but it's a harsh reality when we have to support both systems. That's it for the question.
Super. Well, there's another ECS, at least one ECS question waiting for you in the channel, but we're at time. Many thanks to you, and especially since I know it's quite late in your time zone. So thank you guys for staying up and being cogent. We really appreciate it. So with that, we have completed our last session of the day.
Thank you.
And thank you, guys.
Hey again, everyone. It'd be my job to close out the conference. First, really, I have to say, obviously, a lot of thanks to everybody today. So, I want to first start by inviting my fellow organizers along and to say thank you to them, to Angelo, Stephanie, Natasha, and Mike for all their amazing hard work putting this conference together. There's a lot goes on behind the scenes, many months of meeting to organize things, but it really is all worth it in the end when we kind of put it all together and see everyone so engaged. Also, I've got to say a big thanks to everyone at Activision IT for everything running, so smoothly. I gotta say, like, it gets a bit stressful, before the conference, but Monday night maybe, feeling a little like stressed about what's gonna happen the next couple of days. But last night I felt actually really relaxed. Everything just went so wonderfully yesterday that it was great. And it's really thanks to all these people, to Daniel, Anthony, Chewy, Victor, Christopher, Andre, John, and Nelson. Thank you. We couldn't have done it without you. It's really appreciated. And of course, we've got to give another big round of applause to all our magnificent presenters for their hard work. It really wouldn't be the same, without them and all the work that they put in to the conference. This is basically about them. So to Felipe, Michelle, Max, Kleber, Navjot, Nicola, Hitoshi, Igor, Will, Darren, Joel. Thank you so much. Really, really appreciate all the work you put into your talks and your willingness to share all the tech and also participate and answer all the questions from our audience as well. And finally, of course, really thanks to all of you out there attending. Again, we get so much energy from doing this from all of you. I think, Mike said after last year's conference, something like, we go from 3 hours from saying, we'll never do this again to, we must do it again and really part of that is because of how all of you seem to really enjoy what we're doing and all the engagement you give on Discord. So really thanks to all of you for all asking questions, participating, being really engaged. And we actually got some stats out as well from this, because we put some numbers into some AI and saw who was theoretically most engaged during the conference. And these are a number of people who asked the most questions. So thanks to all of you, and big perhaps a shout out to Tian Ning, who asked the most, 8 questions throughout all the talks. And honorable shout outs there to people like Kay Mishra and Benoit Miller as well, second and third place. Thank you so much for all your engagement. Again, please fill in this survey to help us with future events. That would be really, really wonderful. We do read all this. It's really useful for us. Please help that fill in. And as a reward for filling it in, well, we will be uploading the slides and videos to our website and YouTube channel as soon as possible. I know we have a lot of questions about that. We really will try as soon as we can to get things up there, but please bear with us. We have day jobs and everything, but we'll try our best. Funny, if you like this conference, well, there's more graphic stuff coming up this year. We have HBG coming up this month in Copenhagen. I think even Angelo might be giving a keynote there, so you'll see him again there. We have EGSR as well, also in June, co-located with HBG, so that'd be great. And then, of course, we have SIGGRAPH later in the year, which I know I will be attending. It would be great to be there and see as many of you possible there. I cannot believe it has been 20 years of advances in real-time rendering. That is obviously one of the highlights of the year for all of us in graphics. I realize I've been in the industry for 19 years, so it feels like advances has been, sort of there all the time I've been in the industry. It was definitely one of my bucket list items in my career to speak at advances. I've been lucky enough to do it twice. I'm sure there'll be another wonderful content again this year. And of course, we're bringing back the physics-based shading course again. First time in 5 years, myself and Stephen Hill. So even more games content to SIGGRAPH. Looking forward to seeing you all there. And maybe, there'll be a REACT 2026 as well. So get thinking if you'd like to submit some talks. Have you been inspired? We'd love to have your submissions. And again, thank you all really so much for participating. It's been great. Hopefully see you next time. Goodbye, everyone.